Well, everybody, welcome to the beginning extravaganza of what I hope is a great semester. It is my pleasure to introduce Burr, who talked to us on, not just talk. He's actually not just a talker, but a doer. Because after this, we will have Math Club After Hours, and we'll put some of this into action if you can stick around. But for now, he will be telling us about origami as mathematics.
Hey everybody, hope your semester is starting out well. Great. So yeah, I hope that enough people stay because a dodecahedron has 30 edges, and it's a lot easier if everyone makes one or two than if somebody has to make 10 edges. All right, so first we're just going to start out looking at some pictures, have some fun, and then see where it goes. All right, so when you first think of origami, you think of this, perhaps. Standard paper crane, okay? And if we want to make it mathematical, maybe we just put a bunch of paper cranes in the sphere and we call that math. It's a pretty cool picture, but yeah, that's not what we're going to be doing. All right, so let's start out and talk about, what are some artistic parts of mathematics and that are secretly, artistic parts of origami that are secretly mathematics. So Robert Lang is a well-known origami artist and also a physicist. And there's some stuff that he's done taken from his website, and pretty amazing. So there's the snake. People dancing, playing music. He has a huge collection of bugs. Apparently, he said that when origami people go to a new city, the first thing they do is check out the bug museum and try to get new ideas of stuff to make. So with that, all this is his. Still origami. Kind of crazy. All right, so there's some art, really amazing origami. I recommend you check out Robert Lang's stuff. But he's going to come back into the picture in a little bit. Now, if you think about like mathematical origami, you might think about something like this, which has, well, I guess it's 4 interlocking triangular pieces. Or it might be something like these. Can't throw them too far on the paper. I'm gonna hang on to one. So maybe a cube. Or maybe something like this. I do this with my students in multivariate calculus to see what a saddle looks like. So these are ones that I've saved from the trash, so there's various stages of disarray. But really here for some pictures. Oh, and if anyone wants to learn how to fold any of these, I have instructions here. So if you want to learn how to do them, just let me know and I'll give you the instructions. Another cool mathematically inspired origami. Another one. That one is kind of similar to the hyperbolic paraboloids that are being passed around, except a little more complicated. So that one's by Tom Hull. Tom Hull is a mathematician first and an origami expert second, I'd say. It's pretty close, but he's a mathematician, and the dodecahedron that we're going to make later is from his directions from his website. So another cool person to check out. He's crazy. He often goes to JMM and MathFest. So if you see him there, if you see he's not talking, worth checking out. Another thing that looks very mathematical. And we can get even crazier. All right. So right now, we've talked about, we've looked at some pretty pictures of stuff that you can do with origami. And we look at some stuff that's like math inspired origami. But it goes the other way too. So Robert Lang, the person I showed you at the beginning, the way that he designs his stuff is he developed a program called Treemaker. Okay, and what it does is, well, let's go back. So when he sees something like this bug, he sees it as a tree. Okay, so the body is the center node of this tree, and then there's stuff that comes out of it. All the legs are different edges that come out of the center. The head might be connected to the center, and then from the head, you have things coming out of the head, the wings. Each one of those things is basically an edge or a vertex come in the in some tree representing the bug. So he came up with a way to turn that into a design for origami. So, for example, this is something that his program created. So it sort of gives the structure of how you get it started. And then you have to do the artistry to make it look awesome. But the first step is just to get some folds so you're going to get the object that you're looking for. Anyone want to guess what this is? What?
Crane.
A crane. Any other guesses? I don't remember what it is. So it might actually be a crane. Let's see. It was another bird. So it's an owl. All right. So going back, I believe that these two here, these should be the talons. And then the body is here, and then each of these triangles that's coming off is going to be some pokey thing on that owl, like the wings or something like that. Or the stuff on the head. All of that is captured in this origami design. Okay, and this one's a little bit easier to see. Okay, easier to see. What's happening here is each of these circles represents a body part. So this is the main body, and then you've got body parts up from here. All right, so everyone knows what this is? All right, bud. Probably pretty close. I know what this one is. Any other guesses? Or anyone want to refine bud? The scorpion. So you've got the body, you've got the head, you've got the pincers up there, you've got the legs on the side. You can see all those things here in the final version. So, I mean, there are plenty of steps between this original picture and scorpion, of course. But to start. All right. Once you have the right number of appendages, you can fold it and adjust it and smooth it out and make it look really awesome. Okay. Robert Lang can do that. I can do the first, which is open the software and plug something in. Yeah.
Does the program show you a 3D visualization of it, or is that up to you to mentally?
You have to mentally do that. So it's really just so there's a main body. You sort of have to give it the pieces, the tree. You have to give a sort of crunched down version of your object. So each thing that's supposed to stick out is going to be a leaf on a tree, and then you've got a main body part, and so from all that it comes together. Pretty amazing. It's not trivial. All right. What's this one? And Matt, what's this one?
Brain.
You were just 2 slides too early.
Starting world word.
Okay, you're just playing Wordle on it?
Yeah.
Okay. So it's pretty cool. All right. So let's have some more fun before we get into anything serious. I need 3 volunteers who can operate scissors. Okay, 1 back there, come on up. 2 more volunteers, come on up. Come on up. All right. So each of these things is something I pre-folded, and you'll notice there's a line on it. So please choose which one. What they're going to do is they are going to cut very carefully straight across the line all the way through the paper. Okay, who's first? So the scissors just right on the line, cut straight through it. I'm going to stand away. Do the magic. Yeah, make sure it's all through all the layers of paper. So there's some stuff in the back. This make sure it's all. Okay. Yes. Cut right through the paper. And hopefully I folded these right. I don't have any backups. So if it's wrong, all right. Head over. All right, now can you please, before going on, before cutting, can you please open up your 2 pieces? So turn it. Open up the head. So what did you get? It's a swan. It's supposed to be a swan. It's okay. It's a little bit. It's got straight edges, but it's a swan. Now you can open up the rest of it and hold that up. So turn it. There you go. So what happened is you cut straight across the piece of paper, and you cut out a swan and the rest of the swan and the complement of the swan. Just from 1 cut. All right, thank you. You can have it. Actually, you can have it if you want. All right, who's next? All right, you cut across? Now, what did you get? Did you get some moth? Right. So turn it over. What did you get?
Like a moth with butterfly.
I think it's a butterfly. I'm gonna go butterfly. So there you go. All right, go ahead. So the last one here. Keep going. One more. Yeah. At least 1 more. That's 2 sheets put together. Yeah.
Oh, there it is.
So can you hold it up? That would be a fish.
Oh.
And that is the complement of that. So let's look at this. So let's look. So thank you for the help. Let's do full screen this here. All right. So this is the fish. These are the folds to get the fish. And there's a lot of napkins. So if you start staring at this, you're going to see some things. You're going to see some angle bisectors. So like the edge, this is a you can't mark, but when a fold goes through a vertex, it's an angle bisector then. All right. When it goes through an edge, it's perpendicular to that edge. Okay? And everything here, all the edges that you see are bisectors. Some of them are like bisectors of bisectors, so it might be like, like an edge on the front of the fish, and over here they get bisected, and so there's some of the internal edges can be the angle for them corresponds to a bisector of two edges that are next to each other. All right, so there's that. Let's look at the butterfly again. You see a lot of bisectors here. When you see meeting it inside of an edge, you see something perpendicular. So the reason why you have bisectors and things like that is when you fold along a bisector, the two edges come together on the same line, become the same line. And when you fold along a perpendicular to an edge, the two parts of the edge come together and lie on top of the line itself. So you get something that all the lines will coincide when you do all these sort of folds. And there's actually an algorithm to create these. It's really, I've tried to use it. It's really tricky to use. Right? To not get infinitely many folds takes some serious work. Let's look at the swan. Again, angle bisectors, again, perpendiculars. And there's some other rules that need to follow, so this is going to hold flat, but this is good enough for us. So these three, actually this whole theory, a lot of this theory was developed by Eric Treemaker. And Eric, he is an amazing guy. He is a full professor at MIT, and he was made he's the youngest professor ever at MIT. But he's really like down to earth and cool. So, you hear like the people that, child geniuses, he's one of those, he finished his bachelor's at 14. And you hear about them, you normally think that, you can't relate. He's super relatable. So that's kind of cool. All right. So what are we talking about so far? We've looked at origami just as art. We looked at origami making mathematical things. Okay. We now have looked at math inspiring origami. Is that we use these? Oh yeah. Mind I bring up our name? This was his PhD thesis. Is coming up with the algorithm to construct this. All right. Sorry, I got off topic. But now we have math inspiring origami. Yeah.
What's the algorithm called?
Don't know the name. It's in his dissertation. So just look up Eric Treemaker, MIT, and find his dissertation, and it's in there. All right. But the thing that I want to talk about is rigid origami. So this brings together some math, some art, and some engineering. Okay. So that's actually Robert Lang. And he helped design this mirror for a space telescope. It's got a lot of glass in it. And one thing I know about glass is it doesn't bend so well. Okay, so but it has to fit in the rocket that's going to launch it to space. So this mirror that's used as a space telescope actually folds. And it folds in a way that the glass doesn't bend and break. Okay, that's something that's what we're going to investigate a little bit today. It's called rigid origami. Where else does rigid origami show up? Well, it's a stent that you might use to keep a blood vessel open. When you put it in, it's made of metal. When you put it in the body, it's all folded up and then it expands. All right. Now, Next one, what's another application? I need a volunteer who's going to lose. So Jim, for a volunteer to lose. Can you hold up this map as fast as you can?
I'm not good, that
There you go.
might be in pieces.
There you go. I'll give you a head start. Maybe I should do that one. It's about it. Just unfold mine out
Oh, right. That's
as many times as I want. So if you ever if you ever have a map that's like lives in your car, it probably looks kind of like this, and it's impossible.
Why don't they sell the other map?
They
Why?
do some places
I've never
in
seen the other
Japan.
map, the good one.
in Japan.
Oh,
Yeah, so. Okay, this, if you've ever noticed when you have a map, a paper map like this, it always gets holes in it and rips and things like that. It's not a really good design because it's, when you fold this up, it actually stretches the paper. And paper doesn't like to be stretched. It's not a rigid fold. All right? But this is something called a mirror map fold. And you can open and close it very easily. Actually, you only need just one motion to open and close it. And it's actually, it doesn't stress the paper all that much. Actually at all, and that's provable. So, here you go.
is
So-
there any disadvantage to this?
What?
Is there any disadvantage to this design versus?
So it's a little zigzaggy. The mirror map fold has zigzags. In it. It's
Would
not,
that be bad for a map, I guess, or not?
well, people don't necessarily like that. It doesn't look like, you know, it has a little bit sticking out here and there. But I've seen ones from Japan, and they're just such a slight angle that it doesn't even matter. So where does this get used? So there's some mirror, those are some actual mirror maps. And they're really cool, but they are hard to find. It probably takes more technology to construct it as well. But why is this cool? This gets used in solar panels. So these are mock-ups of solar panels that would use a mirror map fold. And actually, this is one that uses it. And why is this useful and interesting and important? Is that it only takes one motor to open this up. It's got one degree of freedom. So if you're interested in launching something into space, weight matters. Weight, how much something weighs, every pound that you send up, there's a corresponding amount of fuel, a whole lot of fuel that has to be used to send that up into space. Okay, so if you can cut down the amount of motors that you need to open up your solar panels, that's pretty awesome. And so, again, Japanese, but they use this mirror map fold to have solar panels automatically open or with just one motor, and that's useful. All right, so Origami Basics is just the last thing before I'm going to switch to the board. A map and fold is a dash dot pattern, and that means you fold away from you, essentially. A valley fold is just dashes, and that means you fold towards you. If you try to do any of the folds, like the demos that we had of the fold and cut problem, it's easy. Just the way you really do it is you just fold everything that's on the piece of paper and then correct the direction of the folds. Once you make the paper a little bit unhappy, or once you make the paper a little bit damaged, it's easier to fold again. Okay. So if you want to try any of those, that's just a hint for that. So now we're going to get into some math. All right. Any questions on the art and pictures part of the show? All right. So what we're going to talk about is this combination that we just had of engineering, math, and origami. And what we want to talk about is what is rigid origami? What does it mean? So I'm not going to, the definition is basically origami that if you made it out of sheet metal wouldn't tear itself apart. Okay, so how do we figure out that something is a good fold for this? Because you're not going to build a satellite, build the solar panels, and then and all of a sudden just sort of say, all right, let's open it up, everything goes smash, and let's try again. You got to have some way to figure this out. Okay, so this next part, or the remainder of the talk, this is borrowed from a talk with permission, with a talk from Tom Hull that I saw in a class, or actually our domains class that I was sitting in. So we'll turn off the projector. So I do have permission to talk about this. All right. So what's something that's not a flat fold? It's these guys here, wherever they ended up. These are not flat. So if you have those, I think there's a whole pile over there. If you notice, right in the center of them, a lot of them have a rip right in the center. So if you can look through them, do you find any that have a rip right in the center? I think the pink one does.
I can give it a rip.
What?
I can rip it if you want.
No, I don't need a rip. But a lot of them have like a little slice in the center. Does that one have a rip?
It does.
All right, that's actually made out of cardstock, and cardstock doesn't bend at all. So what happened is this is something that paper doesn't like to do. It's has what's called negative curvature, and the paper there ripped because it was so angry. All right, and if this were solar panels, the solar panels would have ripped. Bad design for solar panels. Do not create hyperbolic paraboloids of solar panels. All right. So what we want is we want something, if we want to use this in an engineering situation, perhaps we, and what we want is we want some way that we can fold this up. And it's not going to rip, it's not going to bend, because we might be using a material that doesn't reverse its fold, that doesn't want to stretch, doesn't want to bend. So here's an example of something that's folding rigidly. It's not bent, it's not supposed to be bending at least. But how do I know? Okay. So I'm going to draw this picture on the board. And we'll start talking about it. So the folds that I have on here. It's got something like this. Okay. And when we fold it up, we get a nice corner, and it's all happy. Okay. So hold this up. It's hard to see. Here's the diagram. This is exactly the same. These are exactly the same. Okay. So the square is my big piece of cardboard, and all of these folds are on. Now, if you look through these folds, you might want to see how much angle there is. Okay. So this square right here. This is our bottom square, and we can see the next square is right angles to that. So that's going to be a fold of pi over 2. And then the next one is from the back to the side, another right angle, pi over 2 angle. The next one is from the back down to the bottom, or the side to the bottom, another pi over 2. And the last two folds, they're a little interesting. They're this flap on the inside. And this flap on the inside, you can see it's folded against itself. So we get an angle of negative pi over 2, negative pi, and pi, because it folds back on itself. Okay? All right. So one way that we can start to see whether something is a rigid fold is whether it stretches the paper. Stay. Okay, one folding fine. All right, so think of it if you have a little bug on here. bug could walk around in a circle. That bug could walk around in a circle and, spend a quarter of a circle in this one, a quarter of a circle here, an eighth of a circle, an eighth of a circle, and a quarter of a circle there. All right. And when we fold it up, if there's any stretching, well, that stretching would mean that it went, too far in one of these or too little in another one, and it sort of didn't spend the right amount of time in each of the faces. When it got all folded up, maybe one of the faces, one of the pieces got stretched, and this curve, which used to be a quarter circle, is now something else. So how can we check for stretching? It's actually using some linear algebra. Okay. So the way it works is we're going to have, for each fold, we're going to construct a matrix. And then we're going to put these together. And it's actually pretty simple how we put them together. So we actually need two pieces of information to create these matrices. We need the angle of the edge. And we'll 5 4ths. We need the angle of the edge and the angle of folding. So the numbers that are on the edges are supposed to represent the angle, or the angle from the counterclockwise angle from 0, and the numbers outside of the folding. Yeah.
How do you find the angle of the paper?
Well, I don't know about it.
How do you find the angle of the paper? What's positive, what's negative? What does that mean? The angles?
So fold, it comes from you have to have your final picture, but there is a way to do this. What you're going to do is, say you go, you're on the bottom one, and you say, if I were to keep going, I'd go here, but instead I'm going to go up. So the angle from where I was headed to the actual position, that's the angle of the pi over 2. So if you were to keep going on the back edge, you go here, but instead you do this. And then the negative pi over 2 and pi over 2 is because you're going on the top side, and then you're going underneath of a piece that's just a flat that's folded against itself. So you just turn all the way around. Does that make sense? Yeah. All right. And let's start. So what these matrices are going to be, the rotation matrix, if you were along this edge in the xy plane, by the specified angle. So the first one is 1 0 0 0 0 negative 1 0 1 0. And that's what would happen if you took it. That's the transformation that corresponds to taking this piece of paper and rotating it out of the plane by pi over 2. Okay. So that matrix represents this transformation. And I checked this today, so everything should be good. These should be the other rotations. So each of them, it's like in this matrix, there's a 1 in the middle. That means the y-axis is getting fixed, which is exactly what's going to happen if you rotate along the y-axis. The third rotation is 0 0 1. So is a rotation on the negative x-axis or the x-axis again. The fourth one, that's not going to fix any axes. It's just rotating along the line y equals x. So this matrix is 0 1 0 1 0 0 0 0 negative 1. And you can check all these at home, or you can just believe me. So these 5 matrices represent the individual rotations that we're going to have along each edge. And now we're going to put them together. All right, so we're going to do a sequence, we're going to construct a sequence of matrices. And the way that works is a recursive formula or an iterative formula. We're going to do LK is equal to LK minus 1, LK minus 2, all the way down to LK, oh sorry, L1. And then your rotation. And then back up with inverses. So if you've had some abstract algebra, there's a conjugation going on here, and what's happening is you're undoing some rotations, you're adding a new rotation, and then redoing. And if you haven't had abstract algebra, then you just say, sounds good. Yeah.
But isn't that like the change of basis? Also like different words?
Yes, it is a change of basis. What you're doing is you're taking your coordinate axes and rotating them in the opposite direction of everything that happened before. It's doing your new rotation and then rotating them back. So yes, it is also a change of basis. These are all the same thing. Yeah. Since it's a Friday afternoon, let's just take it, and I'm just going to write it down. L1 is that. L2 is this one. L3 should be 0, 0, -1, 0, 1, 0, 1, 0, 0. L4 is 0, -1, 0, -1, 0, 0. This is just so you can check it at home and know that I'm being honest. L5 is -1, 0, 0, 0, 1, 0, 0, 0, -1. All right. And what Tom Hull proved, and I believe it was with one of his students, is that there's no stretching. Actually, I should say it a little bit differently. So, theorem. So, Astro and Hull. Not sure if it was a student, but what the theorem is that if there's no stretching, this implies that the product of the matrices Ln times Ln minus 1 times all the way down to L1 is the identity. And if you're bored, you should be able to take those 5 matrices, multiply them out, and you should get the identity. Now, yeah, that'll take about the rest of the time that we have. So if you're bored, go ahead and get started on it. This actually also implies, and it was a slightly easier way to work on this, is that the product of the rotations is also negative. All right, but this means that this means that in the final object, no stretching happened. That all the pieces are just the same distances apart that they were at the beginning. Actually, it's not sufficient, it's just necessary. Making faces, just thinking about it.
So I was wondering if they had any kind of work on work.
Well, maybe in a couple cases, but in general, no. So one of the limitations is it's not a guarantee. I'm going to give you an example of where things get a little bit bad. It also doesn't say that it just talks about the final state. So, but you know, when we were talking about it the whole time, there's a whole motion that's going on from start to finish. You want to be rigid. You don't want to have to like stretch things, and then after you stretch them, they become nice again. So this doesn't tell you about that, but it's a step. All right, let's look at another example. This one, I'm not drawing in the direction of the folds, doesn't really matter so much. You try this one, and it's going to work. Okay. Got it folded right here. This is kind of a problem with this one. The problem is, even though it works, see this flap down here? It's supposed to be connected to this flap up here. And the problem is, so the problem is this computation has no idea about paper having size. So the bottom of this one is the same as the top of this one. So it satisfies that rigidity condition, but it's not really good for building anything since it tries to connect through itself. So that's a sense in that converse is that there's limitations. All right. So that's one way that we can use to try to figure out if a folding pattern is going to be rigid. If it's something that we could use and make out of metal, that's going to be okay. I want to talk about one more. This one's the so I've been trying to build up more and more complicated. So this one's the complicated one. All right. So this one uses the geometry. And we'll see why, we'll be able to understand why that the hyperbolic paraboloids are not happy things for paper. So what we're going to do is we're going to use something called a Gauss Snap. All right, and there's other ways to do this, but this is probably the easiest one to get your hands on. So say you have some surface and you're interested in a point right here. So what you do is you draw a loop around that point. Okay, and we're going to fill in that loop. So it's a nice disc type thing. And at every point in that loop, we have a normal vector. We have the vector that's pointing directly out of the surface. Okay? And what we're going to do is we're going to take that and we're going to put it on a sphere. So we take those vectors, those normal vectors, and we're going to just plot them on a sphere. Here's one of the vectors. They do all sorts of things. There's some sort of shape on a sphere. And you figure, I'm going to show you, there's going to be a hands-on demo in a second. And you follow the shape that they trace out. Okay. So we'll call this one gamma and this one gamma prime. And the curvature is equal to There'll be a limit here. Of the area inside the signed area in gamma prime divided by the area in gamma as gamma gets smaller. So we have this region of one side, this region on one side, given by gamma has some area that it encloses. And then when we take all the normal vectors and plot them on a sphere, you get another area. And that the area traced out there is gamma, well, the curve is gamma prime, and the area is the area in gamma prime. These are both signed areas. So if you let these get really, 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 really small, then you get the curvature. Now, why does that matter? Paper is flat. Right. That means it has zero curvature. So if you try to do this computation and you get something other than zero, you're in trouble. It's not, its paper is going to be unhappy. So now, I have one last of these hyperbolic parabolas. And this one, since it's gotten handled a lot, it's also gotten got a lot of pins stuck in it that it's hard to see a little bit. But what happens is, so here's my sphere. Oh, actually, I should have it this way to match what's on the board. Here's my surface. And here's my sphere. Okay. If I make this, sorry, bend this a little more, I've got, what happens is this green one here, it's really hard to see, it's pointing inward, and this purple one here is pointing inward, and the other two are pointing outward. I'll pass this around in a second. Okay. If you go, say, counterclockwise, a loop that's counterclockwise on here, you get the order of green, yellow, red, you get a certain order. And if you plot these vectors on a sphere, so you put them on the sphere, they go in actually the opposite order. The opposite order. So one of them goes clockwise, one of them goes counterclockwise. Okay, and that's indication of negative curvatures. Our assigned areas are going to be negative, and we don't get zero. We get some negative value, and that's why those hyperbolic paraboloids are so angry with paper, and especially with the card stuff, because they're trying to stretch the paper in a way that the paper does not want to stretch. Yeah.
How do you determine what shape the normal vectors form?
Just take the region, take all the points that are given up by the normal vectors, and just take the just build the region out of that. So it doesn't. Well, actually, you can. Sorry, what am I saying? You have the curve in order here, so you just follow that curve over here. Okay. So just follow you take the curve on the original surface, follow it around, and it traces out a corresponding curve on the sphere, and just follow it that way. You have to be a little bit careful if it self-intersects, but other than that, you just sort of follow. You just follow it. It's just like if one moves, like those, the things that like Lincoln had that you could sign one piece of paper and it would sign 6 others. It's kind of cool. If you ever look it up. He had this thing that you could. Abraham Lincoln had this thing that would duplicate signatures, so that you sign once, and it signs 4 documents at once. So it's kind of that same thing. You move the pen in one way, and then it moves the pen on the sphere a whole bunch of ways. So I'll pass this around. Be careful with this one; it's easily broken. Hold the hyperbolic paraboloid underneath it, and use your imagination. So I'll send around a cardstock one, so you can see better. Like some things are pointed here. These go together because you have to. The pins on one and the other are in correspondence, so you can see that one's going clockwise, one's going counterclockwise. Send this around with it so you have a better sense of the shape of where the vector should be pointing.
Are these like unit vectors and sphere range 1?
Yeah. You normalize them so everyone. Yeah.
This might not be like obvious, but is it like a motivation for the definition, like the area? Is it like the intuitive motivation for the ratio periods in the curvature? Or you like keep it from some like starting or principles?
I don't think I have a great answer to your questions. The question is, we've heard is why is this formula even reasonable? So one thing that you might think about is think about spheres of two different radii. Okay, so if you do a small circle on one sphere, on a large sphere, and then map that to the smaller sphere, it's going to be an even smaller circle. So you can sort of think about it that way. Other than that, I don't necessarily want to get into the details or am prepared to get into the details. There is actually, this is an extrinsic way of defining it. There is an intrinsic way that doesn't require mapping or dealing with spheres at all. But this is something we can get our hands on. So what I wanted to show you is, and what we've done is, first, origami is really awesome because it's really pretty. Second, that there's, you can make some cool math stuff with origami, and that's what we're going to do next. Or mapping stuff. But then also that math can inform origami and show us how to create those amazing things that Robert Lang does, or even to design that fold and cut problem, or even to design stuff that goes into space. Is that we have to, mathematics is really helpful for setting this up and understanding what, how to create these or how to design something that's going to have the right properties. That's going to be able to fold correctly and not just, not break into a million pieces when you get to space, because that's expensive, a million pieces. And there isn't a perfect way of doing it, of testing whether something's going to break. This rigidity is going to be okay in space. It's going to be okay folding and unfolding. But there's two ways to get at least a decent idea, like how at a point is it folding nicely. Is there any stretching going on in that? That's one way to check. And this is another way to check, perhaps a better way to check, or better in the sense of better answer, harder to do. So an alternate way to check whether there's any stretching going on. All right. So what we're going to do next, whoever stays, I hope that a bunch of people stay. So what we're going to do is we're going to create a dodecahedron. And that dodecahedron is you're each going to build pieces like this. Little pieces like this. Pretty simple to do. You're going to sign it. Okay? And what we're going to do is we're going to collect all of them and put them all together to make a dodecahedron. Okay, so if we can get 30 people to stay, we're talking everybody gets a unique signature on there, and it's pretty awesome. Okay, if fewer people stay, then everyone who's left has to do more work. All right, and I got some new cardstock today, so we can choose some colors. But that's not my talk. Thank you so much.
Any questions before we pass from the realm of pure mathematics to finite mathematics?
Yeah.
Is the L related to like stress, like physical stress? What is the
L is just what was used in the paper. It has nothing more than a letter of the alphabet that we chose to use. There's no meaning.
What's the difference between L and X?
So the X's were was like the original position. The L is actually what you get when you do the rotation in space. Okay.
I know you said that L process was iterative. How do you get L1?
L1 is pattern. See, pattern. That one doesn't have it. It's just you don't have anything to multiply. You just take the first rotation. You're good, and then from there. All right. Yeah. If anyone wants any swans, I have swans and things like that. I got swans and butterflies and fish and stuff like that. Yeah. If anyone wants to fold them and have some fun with it, go ahead. Yes. All right.
Let's take our finger down and let's do it.
All right. So, all right, let's start this one.
Oh my God. At the See you next week.